Welcome to the second tutorial in Introduction to Spatial Agent-Based Models for Socio-Environmental Systems. The second tutorial will be slightly more technical than the first and dig into the specifics of how agent-based models work. I'm Dr. Nicholas Magliocca, an assistant professor in the Department of Geography at the University of Alabama, and the director of the Laboratory for Human-Environment Interactions Modeling and Analysis. The first goal of this tutorial is to provide an introduction to the core components of agent-based models, or ABMs. We will discuss how each of the components work together to execute an agent-based simulation. To demonstrate, I will use a wide range of example ABM applications, which also serve to illustrate the flexibility of the ABM approach. The core components we will discuss are agents, the variety and forms that they can take, environments, or the mediums in which agents receive information, sensing or perceiving, which include both the information in the environment that agents use and their methods for collecting it, objective functions, which are formalizations of agents' motivations or goals, learning, which is a key process in adaptive behavior, and decision models, which are algorithms that integrate all of the previous components to generate agent decisions. Before describing agents in detail, I want to make a quick clarification. There are several different names for the agent-based paradigm, which essentially mean the same thing, but differ only because of their disciplinary applications. The term multi-agent systems, or MAS, originates from engineering applications. It refers to models of engineering problems that are best solved through coordinated and distributed systems, such as complex design and manufacturing processes. In this application, agents might range from human designers to automated assembly robots. Individual-based models, or IBMs, are essentially agent-based models originating from the ecological modeling field. Just like in MAS models, agents can either be animate or inanimate entities. IBMs are typically used to understand multiple species interactions, such as in a forest gap model. The only real distinction between ABMs and the other terms is that agents and ABMs tend to have agency in the real system, and thus there is more attention paid to modeling cognitive processes and complex social interactions. As is probably clear now, agents can be just about anything: individual fish, people, households, government agencies, or even entire countries. There could be more than one type of agent, such as in the classic wolf and sheep model, but all agents of the same type are identical. Or they can have only one type of agent, such as in the bar goer and the Alfa bar model, which we will discuss in more detail later, but each agent has a unique set of learning rules in this case. Or in this example application of Schelling's segregation model, there can be a combination of inanimate spatial objects, such as these districts and neighborhoods, which track the racial composition of their residents, and purely reactive resident agents that move between neighborhoods based on the composition of their neighbors. Or agents can be active, choosing among several different locational, crop, and water use options in response to changing environmental conditions, like in the artificial Anasazi model. Finally, you can have a combination of all these different types of agents in the same model, such as Nelson et al.'s rotational grazing ABM. A group of agents may also coordinate their behavior to become a collective. Collectives can be social groups, networks, or other organizations or institutions through which agents share information, values, and/or decision rules. Take, for example, Waring et al.'s multi-level group selection model. Agents of any social group can be heterogeneous in their individual beliefs and goals, but members of the same group all share norms for a given level of cooperation. In another example, my model of cocaine trafficking networks through Central America consists of many individual trafficking node agents, but each is a member of different cartel collectives and are only allowed to interact with other node agents of the same cartel. Finally, in McCord et al.'s model, individual farmer agents must coordinate their water use and maintenance activities within community-managed irrigation projects. Agent types can also be empirically defined, for example from survey data with typologies. Agent types can be defined by a combination of shared attributes and/or behaviors. Each agent type within the typology can then be assigned different goals, values, or decision rules. For example, some farmers may be profit maximizing, while others might just aspire to meet a minimum level of productivity. Valbuena et al.'s regional scale land use model provides a good example. Applying a classification tree to information about farmers' production strategies, farmer typologies were derived based on farm size and expansion and crop diversification strategies. In another example, Fernandez-Mena's integrated food system model, a farm typology was derived based on their main production activities, such as dairy cattle versus horticulture, because each farm type generated different types and volumes of material flows, which interacted with other agent types in the food system. Finally, there's a relatively new concept of agent functional types. These are similar to typologies, but agents are differentiated by their competitive interactions with other agents across heterogeneous environmental conditions. Agent functional types are based on the ecological concept of plant functional types. Briefly, multiple species can coexist in the same environmental space, but they compete more or less effectively across the varied conditions observed in that environmental space. Where a particular species is the best competitor, that species will dominate, and vice versa. This concept has been extended to agent-based models, particularly in the context of large-scale land use change models. At large scales, it may not be feasible to represent the full range of individual agent types observed in a particular landscape, but rather represent the land uses that compete for space in that landscape. Different agent functional types may outcompete given demands for its production, whether cash crops or ecosystem services, subject to market conditions and/or land use policies. Next, let's look at how environments are represented in ABMs. The environment is the medium through which, or in which, agents interact. The environment structures agents' interactions, for example by influencing the probability of any particular agents interacting, and thus is an important influence on the system-level behaviors that can emerge. If spatial relationships have an important influence on agent interactions, then the model environment should represent those relationships in some way. For example, distance from a coastline may be a key spatial relationship for agent interactions and decisions. One could represent this with an actual GIS layer that provides representation of the real shape in two-dimensional distances. Or the model environment can be abstracted to represent only the relevant one-dimensional spatial relationship of distance from the coast. The decision often depends on the purpose of the model, which is a much wider topic of discussion beyond the scope of this tutorial. One reason to choose the abstracted model, though, for example, would be that one less spatial relationship needs to be considered when interpreting model results. Spatial relationships may also be implicitly or explicitly represented in a model. Let's look at an example of an implicit representation of spatial relationships. Josh Epstein's 2002 model of emergent civil unrest provides a good example. The main decision made by agents is whether to actively protest, which is dependent on each agent's internal dissatisfaction level and spatial proximity to another dissatisfied agent. The decision to protest, turn red in the visualization here, can also be deterred by the proximity to a law enforcement agent. In this example, agents move around in an abstracted space randomly, and importantly, that movement does not cost them anything. For movement, at least, there's no spatial relationship represented between distance of movement and an agent's state, for example, its energy or dissatisfaction level. However, the change in an agent's protest state depends on the states and types of other agents in close proximity, which is presumed to be a key spatial relationship. The monkey foraging model provides an example of a spatially explicit model. Trees of different sizes and fruit productivity, here represented by the green circles, are randomly distributed across an abstracted landscape. The monkey, tracked with the white line, uses an optimal foraging decision model to navigate around the landscape by finding sufficient food without running out of energy. Spatial relationships are represented explicitly because the distance between trees is meaningful, as each movement by the monkey costs it energy and is proportional to the distance traveled. It is also important to note that this is still an abstracted environment. A model can be spatially explicit without representing a real environment. There are also many ABMs that do not include spatial relationships, but rather the interaction environment is structured by non-spatial networks. Non-spatial networks provide a structure for non-random interactions among agents. Interactions may take the form of information, material, and/or influence flows. For basic primer on social networks and ABMs, see Hamo and Gilbert 2009. The network structure determines who can interact with one another, and potentially how frequently and intensely. Network interactions typically depend on proximity between agents within the network. That network may or may not be directed, in other words, allowing one-way or two-way interactions, but it structures the interaction environment and influences the outcomes of those interaction processes. In this example, any agent's decision to cooperate, marked with a C, or defect, marked with a D, is a function of the number of immediate connections to cooperating and defecting agents. This is an example algorithm of how social norms can propagate through a network. Increasingly, interaction networks are being combined with spatially explicit model environments to simulate richer spatial behaviors. For example, my colleagues and I developed an agent-based model of cocaine trafficking through Central America. The model represents individual trafficking node agents and agent collectives of drug cartels, which respond to counter-drug interdiction agents throughout a spatially explicit trafficking network. Here, the distance of drug shipment movements along the trafficking network influences the cost, profitability, and risk of those shipments. Geographic relationships throughout the trafficking space are also represented. Trafficking nodes are located in suitable locations based on proximity to international borders, rough terrain, and remoteness from population centers. In this example, there are multiple spatial relationships, both landscape and network-based, that influence agent decisions and interactions, which are represented with a directed spatial network and a GIS-based landscape. Importantly, as I noted before, representation of the environment depends on the purpose of the model. The realism of the environment should be based on the detail of interactions to be simulated. For example, many movement-based ABMs, such as pedestrian, evacuation, or transportation models, need high-fidelity environments to produce realistic movement behaviors. Agents have rules for navigating the built environment and interacting with other agents, such as avoiding obstacles and collisions. The emergent result shows how crowds evacuate confined space, areas of congestion, and overall evacuation time. Now that we have discussed various representations of agents in their environment, let's turn our attention to how these two components are dynamically linked in ABMs. To structure this discussion, we're going to use the MoHub framework, which presents a general structure for behavioral models in ABMs. Each individual agent has the ability to sense or perceive conditions in the environment. An objective function is used to evaluate the current state of the environment and the agent relative to the agent's internal goals. The objective function may evaluate one or multiple behavioral options relative to current conditions and provide metrics for selecting among potential options. That evaluation may or may not be informed by learned experiences of the relative importance and performance of each behavioral option. The ultimate selection among behavioral options is done using one or more decision algorithms or decision models, which may be informed by behavioral theory. Let's start with sensing. Depending on the environment, there are various ways agents can receive information about the environment. In non-spatial contexts, agents may assess information from immediate or more distant network connections, either in direct contact or communication or through virtual networks, such as social media. In a spatial context, agents can have different discrete neighborhoods over which they can access information. For movement-based ABMs, that spatial neighborhood is dynamic, updated as the agent moves through space and changes direction. Agents can also sense features in the environment relevant to their decision-making, such as the location of natural resources or terrain to be navigated. Agents may also have access to common repositories of information, which do not require them to directly observe states in the environment. For example, houses for sale and their price information might be available to agents, just like websites like Zillow in the real world. Agents may also pay attention to emergent system-level flows or outcomes that influence their behavior in the future. The NetLogo model of the L4L bar problem provides a famous illustration. As the story goes, this is a real bar in Santa Fe, New Mexico that plays live Irish music one night a week. However, it is a relatively small bar, and so it can become overcrowded easily and the experience of the live music diminished. Agents can perceive any given week's attendance either in person or reported in the local newspaper. Agents observe the past week's attendance on live music night, form expectations of how many people will attend the next live music night, and then decide whether or not they will attend based on the expected attendance. Of course, expectation formation and subsequent decisions to attend are subject to heterogeneity among agents' preferences, experiences, and methods for making predictions. This is a relatively simple example, but such an agent sensing of the overall system state can easily be extended to the socio-environmental system context for things like crop yields at the end of a growing season, water supply from a public source with multiple users, or fishing catch in a competitive fishery. Finally, agents can also pay attention to the patterns of behavior of other agents. Let's take a look at the process of cooperation with an example model. This model implements an iterated prisoner's dilemma in which each grid cell represents an agent that can play one of 15 strategies at each time step. An agent interacts with the neighboring agents in the 4 cardinal directions. Just like the classic prisoner's dilemma, each agent's payoff depends on their strategy and the actions of other agents. Over many time steps and repeated interactions, the tit-for-tat strategy, colored in orange, emerges as the dominant strategy. In this simplified version, agents all have the same attributes and suite of strategies. But you can imagine how introducing heterogeneity among agents would quickly lead to more complex behaviors. Although simplified, this model's framework for simulating the emergence of cooperative strategies has already been adapted to socio-environmental problems. Next, let's consider objective functions. which are an important model component guiding agent behavior. Objective functions are a mathematical or algorithmic representation of goal-seeking behavior, or first principles. Many are based on behavioral or economic theory, such as utility theory, optimal foraging theory, or livelihood theories considering household labor budgets. For example, the utility of a house for consumer C and location N depends on the consumer's income I, net of the asking price of the house and travel costs to and from the house's location, as well as the square footage H of the house and lot size L. This utility can then be calculated and compared across multiple houses. One or more objective functions can be implemented in an agent's behavioral model, and there can be substantial heterogeneity among agents and how certain factors are weighed. In the example above, some housing buyers may place more emphasis on square footage rather than a big yard. Typically, all agents are given the same objective function to simplify interpretation of model results, but some ambitious models have begun exploring the implications of different objective functions within an agent population. A unique feature of agent-based models is the ease with which agent learning, and thus adaptive behavior, can be incorporated. Learning is defined as either individual or collective changes to decision rules in response to changing conditions. Individual learning by an agent can be achieved either through direct experience or shared information, among a social network, for example. When agent collectives are represented, all members of the collective can receive shared information to update their own decision rules. Learning is closely tied to whether agents have memory. If agents only remember outcomes from one time step in the past, they will be myopic learners. The length of memory can be extended and varied among agents to produce richer learning behaviors. There are a variety of learning algorithms used in ABMs, but I'm going to focus on two of the most common. First is reinforcement learning. An agent takes an action in its environment in time t and observes the outcome, either later in time t or at the beginning of t plus 1. An agent then evaluates the outcome against a goal, perhaps using an objective function. The behavioral action is then rewarded or punished according to its performance relative to the goal. If the agent's state was improved relative to the goal, then behavioral options are rewarded and the action repeated in the next time step. If the agent's state was worsened, the behavioral option may be discouraged in the future. In more sophisticated models, there may be a collection of behavioral options that are repeatedly evaluated against observed outcomes, and the most successful option each time step is selected. In fact, this is the type of learning algorithm used in the L4O-bar model that we covered earlier. Another common category of learning model is belief-based learning. Here I'm showing an example of Bayesian learning, but belief-based learning need not take this form. The probability of a given outcome of one or more behavioral actions is estimated based on prior beliefs about the probabilities of those actions, derived from past observations. These probabilities can then be used to weigh different behavioral options and are updated dynamically with new information. Both of these algorithms reflect elements of how people really make decisions based on previous experience or information. Finally, we come to decision models, which integrate all the components we have discussed to select a behavioral option. There are many different flavors of decision models. The choice often depends on disciplinary perspective. For example, optimization, which includes approaches like profit and utility maximization, is commonly used in economics and engineering. Satisficing is a variation optimization that recognizes the limitations imposed by bounded rationality. In other words, it is too costly or otherwise infeasible to fully know all possible behavioral options from which to choose, so a more realistic approach is to select the first behavioral option that satisfies a certain goal or decision criteria. Another approach uses decision-making heuristics. These are often implemented as a series of if-then statements that select a behavioral option based on current conditions. For example, here's a labor allocation heuristic that I've used in the ABM of smallholder livelihood strategies. At each decision point, represented as red diamonds, the farmer agent assesses its current state and relative value of livelihood options to sequentially allocate a labor budget among multiple activities. The same algorithm is used each time step, but the agent's internal state and relative payoffs of each activity might change at each time step. Another common framework is that of the theory of planned behavior. Many theoretical behavioral frameworks can be difficult to implement in ABMs because they have not been formalized in a way that is conducive to their translation into model code. However, there are a number of ABMs implementing the theory of planned behavior. The ultimate behavioral option considered is contingent on several other factors that can be measured through surveys or behavioral experiments. These factors are then combined to estimate a probability of executing the given behavior. One final example is the use of prospect theory to simulate risk-averse decision-making. Prospect theory asserts that decision-makers assign more value to losses than to gains. Applied to a value derived from an objective function, say for utility or profit, behavioral options would be evaluated based on expected changes in value relative to a reference value, which is often the agent's current or aspirational state. Each of these decision models offers a different way to integrate information agents sense and evaluate with objective functions to make intentional selections among potential behavioral options. That brings us to the end of the second tutorial. We covered the core components of agent-based models and how they're integrated to operationalize agent decision-making and behavior. A key takeaway is that agent-based modeling is a remarkably flexible modeling approach capable of simulating a breadth and complexity of behavior comparable to that observed in real socio-environmental systems. Because of that, a word of caution: ABMs can quickly become as complicated and their behavior as complex as the real systems under study. At that point, the model often loses its usefulness as a research tool. Thus, simplifications in one or more of the core components we covered are common and indeed advisable. For further information or more details on topics I covered in this tutorial, a list of references is provided. I hope this tutorial was useful, and thank you for listening.